Hello, my name is John Poolton, and this is my project design for a crib monitoring system for Electro Circuits and Devices 1 at Oakland University. So let's get started by talking about what we got going on here. First of all, here are our node voltage references that are used throughout the schematic. We got positive 12 volts and negative 12 volts here, which are used for the op amps. We have a 5-volt source. We have a 3.5-volt source, which in practice will be made with a voltage divider circuit, which is shown in the report. And then here we have the reference voltages for the heart rate and the breath rate or the respiration rate that is used for the comparator circuitry over here. So to begin, let's take a look at stage one, which we have an active low-pass filter as well as each of the 10 sensors. Sensor number one has 100 millivolt amplitude and it's set at the average healthy heart rate frequency, which is 12K. The frequency range for a healthy heartbeat for this project was deemed to be between 9 and 15 kilohertz, so 12 indicates a perfect healthy heart rate. Here we have sensor number two, 100 millivolt amplitude as well. We have 3.2K for the frequency, which is the center frequency between um, 2.4 and 4 kilohertz, which was the healthy range for the respiration rate. And then the rest of the sensors here are each 10 millivolts at 70K to represent the high frequency noise of the circuit. And so to begin, we got a low pass filter right off the bat using this op amp setup. So this is going to only allow frequencies below 20 kilohertz to pass cleanly. And so after that, we get rid of all this high frequency noise. Now we move on to the signal adder. So we're going to combine all 10 of the sensor amplified sensor readings, and we are going to sum them together here. Note that each of these op amps is configured in a non-inverting configuration to get high input impedance. RS1 here represents the internal resistance of each sensor. And so this summing or signal adder here, non-inverting configuration, it's got each signal has a 10K resistor here, and the gain is actually going to be 90 over 10, which is 9 plus 1. So it's going to be a gain of 10 in order to compensate for the weighted averaging effect that these signals have when they come in. So when they come in, it's going to be all the signals added divided by 10. So that's why we got to put the gain back to get the actual total output of all the signals here. So then we reach this point and we have all our signals added together. Now we're going to enter the active bandpass phase where this top half here is the bandpass filtering for the heart rate channel, and this bottom half here is for the respiration channel. So we're going to take our total signal here, we're going to input it in both of these filters, and this is the low pass, this is the high pass. Both of these filters are centered at a cutoff frequency of um, 12 kilohertz for the heart rate because that's the center, and um, 3.2 kilohertz for these. That's why the components are the same throughout. So we got like 1 nanofarad, 1 nanofarad, 50K, 50K, And then we got the same thing here, but flipped since it's a high pass, we got 50K, 50K, 1 nano, 1 nano. Now, so just these two make up one bandpass filter here. I have cascaded a total of 4 of these in order to completely just isolate the signal that we're looking for. And this has done a really well job at doing so, as we will see when the simulation begins. So after the bandpass filtering, we're going to get just our heart rate signal out here. We're going to get just our respiration out here. Now, we're entering the precision full wave rectifier part of the circuit. It's going to take this AC signal here and it's going to convert it into a DC signal out here. Well, not a DC, but a rectified signal right here. Now, the way this setup works is these diodes make it such that the total output here is going to be the absolute value of the input here. The math is shown in the report how it does this, but we're going to have a nice rectified signal at both of these points. Now we enter the smoothing low pass filter. The smoothing low pass filter is going to smooth out that rectified signal and it's going to turn it into as close to DC as we can get it here. And so after we get our DC signal here, we're going to compare it with the reference for the heart rate. So the reference for the heart rate and the reference for the breath rate or the respiration were both found to be 1.5 volts. And at this number, we are outside of our healthy range of 9 to 15 kilohertz and 2.4 to 4 kilohertz. So as long as our signal is above 1.5 volts, we're going to get a nice healthy output here that's going to turn on and tell us, hey, the heart rate is good, and same with the breath rate here. If it's above 1.5, we're going to get a plus 5 volt output here. And so then we're going to move on to this summation of signals here, which is technically one stage if you look at this comparator here with these, because this is once again another weighted average summing amplifier configuration, although they are comparators, and the LT1720 was selected because of its high switching or its high speed and its ability to have push-pull action with its output. So a pull-up resistor was not needed in this configuration. So as our signals come through here, we're going to have 5 volts here, 5 volts here in the healthy condition. As they come through here, they're going to be halved, and so our total here is actually going to be 5 because it's going to be 10 divided by 2. Now, because of what's happening there, that we're getting a 5 volt signal here for both healthy, we have set the reference voltage here to 3.5 as a nice average between 0 and 5, between 2.5 and 5, such that if both signals are on, we have 5 volts, which is above 3.5, and we get um, a positive 5 volts here at the output, which indicates a healthy condition. Now, if either one of these signals drops low, we're going to have 5 volts coming in or 0 volts coming in. This is going to sum and divide by 2 to be 2.5 volts, which is below 3.5. So we're going to get an output of a low 0 volt condition, which corresponds to an alarm and there's something wrong, which should be the case since we need both of these conditions, heart rate and respiration rate, both need to be healthy and they both need to be met in order to prevent the alarm from going off. So and also if both of them are giving zeros here, well, of course we're gonna still get a zero and we're gonna get an alarm. So this operates as an and gate essentially. Both heart rate and breath rate have to be healthy in order to have no alarm. Now, let's go ahead and simulate this. Okay, so a key thing to keep in mind here is we're beginning the simulation at healthy conditions. We have 12K and 3.2K, which are both the healthiest options that we can have here. So let's begin by checking out what the output of the first op amp looks like here for the heart rate signal. Now, the sensor reading, as you can see, is 120 millivolt peak here. Um, well, sorry, it's 100 volt amplitude, 100 millivolt. And if we compare this to the output here, we're going to see we get the exact same signal, but now it's amplified up to near 5 volts, as close as we can get. And so if we now look at the same thing over here for the breath rate, we can see that our breath rate's at 100 millivolts, same as our heart rate, although the frequency is clearly different if we compare it to um, the heart rate in green. But let's go back to the respiration for a moment, and let's look at the output of this low pass amplifier here. So our red was our sensor reading, our green hits all the way up to 5 volts, which is perfect. Now, if we compare this to the 70 kilohertz noise, we're going to see that, first of all, our noise is a much higher frequency and it's at a lower amplitude here. As we go through this low pass filter, we're going to see something interesting. So actually, the output here in green of the noise does get slightly amplified at about, let's say, it goes from 10 to about probably 95 millivolts here. So it does get a little bit of amplification, but not nearly as much amplification as the correct signals below the 20K get. Now, it's important to compare these two results. So if we can put all three outputs here, we have in red the heart rate, in green we have the respiration rate, and if we look at the noise, it is very small at this point, and it's going to get filtered out even more as we progress through the circuit. But for the sake of this low pass filter, uh, mainly what it does is it amplifies the signals we want, and it barely amplifies the noise that we don't want, instead of actually completely cutting it out. Now, if we proceed on to the summing amplifier here, we're going to notice something interesting. So when we sum these all together here, we get a crazy looking wave here that has a little bit of noise, not much, and it also has the heart rate and the respiration rate mixed in here, all into this one. So as we go through this signal adder, we're going to see that it's going to once again amplify it because we're now at 1 volts, um, and we're going to get up to near 10 volts here because each of these important signals, the heart rate and the respiration rate, both take up about 5 volts. That's why we have a total amplitude nearing 10 here. So as we continue through, we're going to go take a look at the first bandpass here, and we're going to see something. So this is the heart rate bandpass. We already, after just one filter, get a very nice, almost perfect match to the original signal here. But it's not perfect. And so we go ahead and if we look at the end of this bandpass here, we're going to see, and we'll compare this to the original signal here. Now it's near perfect, and it's also staying at 5 volts or about 5 volts. If we take a look at the respiration rate, we're going to see the input coming in, the total sum of the voltages, and we can go ahead and take a look at the first bandpass here. It's a little bit worse, but it's not bad. If we compare that to the original reading here out of the low pass filter, it's a little bit off, but it's still pretty good. But if we take a look at it in comparison to its final state after 4 stages, we get a near perfect match once again, and we're staying at 5 volts just like we wanted. Now, we're going to continue on to the rectifier here. If we take a look at the heart rate input coming into the rectifier, we have an amplitude near 5 volts. Our output is going to be a nice, not perfect, but a quite nice rectified signal here. This signal does slightly dip below 0 volts and go negative occasionally due to properties of the full wave precision rectifier here and the diodes, but this is going to get compensated for when we get to the smoothing low pass filter. So as we approach here and we check out this voltage, we're going to see something quite well here. So we got a nice flat DC signal now. We do have a slight voltage drop from near 5 down to about okay, well we got to zoom out a bit here. So it takes a little bit of time for this capacitor and this filter to charge up and get perfect up to its DC level. It takes about 50 milliseconds or so from the point of beginning the simulation, which isn't bad um, in real life because 50 milliseconds is a very short time, and by that time we'll get our alarm. But as we take a look at this signal, so our heart rate at a maximum is going to be near 2.5 volts, I believe. Let's see here. We have about 2.5 volts, and this is going to be our best, healthiest signal here. If we take a look at the same rectified signal for the respiration rate, we're going to see it's got a little bit better of a value here. It's a little bit higher voltage, and the reason for that is because the 3.2 kilohertz is much lower of a frequency than the 12K. So in this initial stage, the 3.2 actually gets amplified a little bit more. So by the end of all this, it is going to be a little bit higher, but our noise is entirely gone. Now, at this point, we're going to take these two outputs here, which are respectively 2.46 volts for the heart rate, and we have um, about 3 volts for the respiration rate. Now, we're going to take these two signals and we're going to input them into these comparators here. So let's go back to just our heart rate for a moment. We're going to compare this with V heart rate, which is 1.5 volts. Clearly this is above 1.5 volts, and so our output is going to run high. And as we can see, our slight delay here from when the circuit began, it take about 8 milliseconds before it registers as high. Now we have our high signal, 5 volts. The same is going to be true for the respiration rate. As we compare to our 1.5 volt reference, we're going to see that after about 6-7 milliseconds, we get an active state here for this comparator. So now we have 5 volts for the heart rate, which takes just slightly longer than the green respiration rate signal, barely much. And so as soon as both of these signals turn on, our adder, and you're going to see this visually here, when the green um, respiration rate turns on, we go up to 2.5 volts because of this weighted adder. As soon as our heart rate goes on as well, we go back up to 5 volts at our output here. And this summed voltage, the sum of these two comparator outputs, which corresponds to both a healthy heart rate and a healthy respiration rate, is going to be compared with the threshold value of 3.5 volts. And as soon as we hit 5, we know that we are healthy. So our alarm is not active, but it is at a high 5 volts because in this project, a low output corresponds to an active alarm condition, and a high output corresponds to a inactive alarm condition. So we are healthy for this entire time. Now, let's go ahead and change up some of the parameters to show how this circuit actually functions and what might happen in different case scenarios. So the first thing we're going to do is we're going to change our initial heart rate frequency and simulate as if the baby was getting a low heart rate. So let's go ahead and hit a an 80 or sorry, an 8K, which would be just outside of our 9 to 15K range. And let's go ahead and simulate this. Now, right off the bat, as we wait for this to finish here. So we're going to see something. We can see the working function of the low pass filter here right away. We're going to have a higher uh, output because our frequency is a little bit lower, but everything else is going to stay mostly the same. We can take a look at this sum over here, which once again we have this nice looking graph, but as we look at these low pass filters, we're going to see that, or sorry, these band pass filters, we're going to see that we're only reaching about 1.7 volts now for our heart rate. And that is because, actually, let's give a perfect number for this. We're reaching about 1.5 volts here. Now, that is much less than the healthy range of 12K. And we can compare it to the output of the still healthy respiration rate signal, which is much greater than this unhealthy signal. And ideally, they would be the same in the healthy condition, but this is how this circuit works. So if we go ahead now and take a look at our output of our precision rectifier for the 8K frequency, which is outside of the range, let's just go ahead and look at the smoothed voltage level here. We now have a an output of 1 volt, which is much less than the 2.5 that we had earlier. So that's where this 1.5 threshold comes in, is because now we're well below the 1.5. We're going to get a 0 output here from our heart rate comparator, and let's get rid of some of that. So in the green is our heart rate, which we can see it's flatlined at 0, and our respiration rate is still healthy. Now, when we sum these together, we're going to see that the weighted sum is going to hit a 5 volt plus a 0 volt, and divide by 2, we're going to get 2.5 volts right here. Now, this means that the heart rate is in danger, it's low, and the respiration rate is still healthy. But the whole point of this alarm system is that if either one of those conditions is danger, in danger levels or outside of the healthy range, we get a 0 or near 0 alarm output here. So if we take a look at what's coming in, we have only 2.5 volts. Or sorry, let's go. So we have, those are our two comparator readings, and we still get 0 volts because we need both conditions to be met. Now, let's go back and let's try the same thing, but with a higher frequency that is just slightly outside of the range. Let's try, you know what? Let's display how nice this thing is. Let's go ahead and do 15.2K. This setup we have here is so accurate that even just barely outside of this 15.2K range, we're going to see that the alarm still goes off. And that was important to me because I wanted this circuit to be very accurate at making sure the infant was in the healthy range for its frequencies, for its heartbeat, and its respiration rate. So let's go ahead and simulate this this new frequency, which is just a little bit too high, indicating a rapid heart rate for the infant. And so let's go ahead and just skip all the way to the end now because we have been through this multiple times now. But we're going to see that this output for the heart rate is now just below 1.5 volts here. And of course, due to noise in a real world, this 1.5 might not uh, activate here, but that's okay because 15.2K is just barely outside of the range. Um, it shouldn't activate necessarily until we get maybe towards 15.5, 16K. But we're going to see that in simulation, this does work. It is below the 1.5 volts here, and so we do get a 0 reading, even at a 15.2K, which is just outside the range. So same thing is going to apply here. We have still uh, a healthy respiration rate. We haven't adjusted that yet. We have an unhealthy heart rate, and so our alarm goes off and hits near 0 volts, about 100 millivolts. Now, just for proof that both the heart rate and the respiration rate versions work, let's go ahead and take our center frequency for our respiration. Let's take it to 5K, which corresponds to a high respiration rate, just outside of the 2.4 to 4K range. Now let's go ahead and simulate this, and we have reverted our heart rate back to a healthy condition at 12K. And so as we see with this output here, it's staying down at 170 millivolts, approximately 0 volts. It's a low condition corresponding to an active alarm. If we take a look at the outputs of the comparators, yet again, we see that our respiration rate in red stays at 0. It never turns on because the respiration rate is too high. And so we need both conditions to be healthy to in order to prevent an alarm, and we don't have that, so we get a low condition at the alarm, which corresponds to um, an unhealthy state, and it's an alarm. And so outside of that, that is the main guts and performance of this circuit here. We can take one more look at the rectified signal for um, just outside of that healthy respiration rate, and we can see that we reach about 841 millivolts at our smoothened signal here, which is well below the 1.5. So this filtering setup is actually even more accurate than the heart rate um, is. But overall, I believe this has been a sufficient demo of my circuit. And if there are any questions, please give me an email or um, give me a message or call me out in class and we'll talk about it. But this has been a fantastic experience designing this project, and I've learned an awful lot, and I've gotten much better at LTspice than I was when I began. So thank you, Dr. Sebi, for taking the time and watching this, and I hope everything makes sense. Thank you.